he has a fever and is being responsible and not coming to class. Okay, so here we are. We start out here before anything happens, okay? This is a new one, we'll talk about this in a minute. This is called the decompression strain. So before we even get to the strain diagram over here, we have to decompress the concrete. Now there's another, like I said, there's a diagram on the next page that talks about it, but before we get to this stage, which starts at 0, we have to decompress our concrete. We have to get to a point where there's no strain in our concrete. That's it, to get to that point right there. So that's this epsilon to PD. And then we strain it like this afterwards. Right? We stretch it even further. Okay? And so the total strain we need to calculate. So you can imagine as we're going through this we're going to know. We know what the pre-stressing strain is. Then we have to calculate what this decompression strain is. And then epsilon sub PU is going to be dependent upon where our neutral axis is. So as part of our calculation, we need to calculate all 3 of these. This one's a function of x, but all 3 of them will tell us where we're at on the stress strain diagram. And then once we know where we're at on the stress strain diagram, we calculate FPS. Right? So that's kind of our path forward, if you see. Okay. So I don't know why I wrote equilibrium here. So part of our solution method is we have equilibrium. We have to apply equilibrium. What we mean by equilibrium, we say C is equal to T. Right? That has to happen. If the compression force is not equal to the tension force, then it's accelerating and things are failing and stuff like that. So we have to impose equilibrium. We make this happen. C and T are functions of x. Okay? And so we need to solve for x. For that neutral axis. Right? That's kind of our path forward, right? T is going to have x in epsilon sub pu, and then C, we already saw where it's going to have the x in it. It has x built into it. Right? So it's on both sides of it, and that's what we try to solve. Okay? Like I said before, once I know what this total strain is, all 3 of these things added together, when I know what all those are, I need to then calculate what FPS is given those strains. That's where the constitutive model comes in. So, have you guys talked about that in any class, about how to solve any structural engineering problem, you need equilibrium, constitutive, and compatibility? Remember that? You ever heard that before? That's true. You need all 3 of those things to solve any structural engineering problem. But anyways, here they are here, equilibrium, constitutive model. Constitutive model is if I give it a strain, once I know that strain, I can calculate what the stress is. And so the one we're going to use in this class is what they call the Minigato-Pinto model. And the way that it works, right? Here's an equation for what your stress is as a function of your strain, right? So this is F as function of epsilon. What that constitutive relationship looks like for elastic is just E times epsilon gives us F. Right? The stress is equal to the modulus times the strain. But then when it's nonlinear, you got to do it a little bit. It'll also make more sense when you dive into it. Okay. So this is an equation that we're going to use. We need this because if I give it epsilon, we're going to get epsilon from the diagram above. It's going to be epsilon sub PE plus epsilon PD plus epsilon PU. Those 3 things added together gives me this epsilon. I take that epsilon, I put it into this equation right here. It comes up, it gives me what my stress is going to be. Sigma in this case is our stress. So we calculate our stress based on that epsilon using that constitutive model. Okay? So let's talk about those strains. We call them wonky strains. They get confusing. And this is where Stanton tries to talk about them a little more clearly. He's got a diagram. I think we're going to make improvements. I struggle with the diagram a lot. And then now I get what he's trying to say. So there's 2 different axes on here. One axis is this. It starts over here. And it's positive this way. And this is what our steel strains are doing. Epsilon PS. So my steel down there, right? It's being stretched. It's being stretched this way to the left, and that's being positive. The other graph that's happening is its axis is here, and this is what the concrete is doing. Yeah, positive to kind of to the right there. It's how we're calling it. So the stuff to the right is going to be compression, and the stuff to the left is going to be tension. In this case, it violates our positive negative sign convention thing. But just for discussion here, we'll look at this. So right at the very beginning, right when you've stretched it out, you've cast your concrete, you've released it, and it squishes in a little bit. That's going to cause the concrete to go into compression, right? More compression at the bottom, less compression up at the top. And my steel will be stretched to what we're going to call epsilon sub PE. So that's what this state is right here. I'll try to highlight it here. That's that state right there. Right? That's the concrete right at the first release. And so this is what the stresses in that concrete are going to look like, right? More compression down here at the bottom, right? Less compression up here at the top, right? And if you can imagine, if you stressed it enough, you could end up with tension up at the top. But in this case, we're just going to say that it's, just less compression up at the top. So that's the first state. And when you do that, when your concrete's in that state, my steel is stretched out to epsilon sub PE, right? What we're calling epsilon sub PE. Stanton calls it epsilon sub P1. I'm going to call it epsilon sub PE. So it gets stretched out to that. Okay. On the other side, so that's what that state is. This state right here, that is at the ultimate capacity. This one right here, this is where it's at. This is 0.003. Right, this is my distance x. Right, and then this distance here, from here to here, that's what we were calling epsilon sub PU. Right, the ultimate, right? It's based off of that triangle. So in that case, my concrete, right, is going to be strained out to 0.003. My neutral axis is x, and I can calculate with similar triangles. What that strain is there. But when I do that with similar triangles, it's assuming that my concrete is at 0 down here at the bottom, right? That triangle starts from this being 0 at this location. After I've just pre-stressed it, it's not 0. It actually has stress in it. So I need to calculate, I need to move, this is where this next one is. I need to move this one to 0 so that this number is accurate. Okay? And that's where that decompression is. I have to move this thing over that. Brandon, you're having trouble, man. Yeah. You're having trouble. It's okay. This is pre-stressing, man. This is fantastic. What's that?
It's the mask.
The mask gets you. It just brings you.
It makes it difficult for me to read.
You guys know Sam Wilkes? I don't think you do know Sam Wilkes. Anybody overlap with Sam Wilkes? You might. It's what's crazy about this. It's like people come and go so quickly. Like Sam Wilkes used to sit right in the front, and he'd fall asleep in class every single time, right in the front of class. He wasn't ashamed at all. He just sat there and just everybody just be quiet. Everybody quiet. Sam's taking a nap. The other person that is bad at it, Flynn. Flynn was always sitting in my class too, and she just sit there. Makes me feel real good when I have that effect on the student. But I understand. I have been there and done that before. Okay. So there's this one right here. So this is epsilon sub PU, right? It's stretched there. I have to get it to a 0 state to begin with. That's what we're calling epsilon sub PD. And that's what I've. If you read through his description of it, that's the one I've always had trouble with. It's like, why do I have to get to that zero state? Like, why can't I just go, it's just going to be epsilon sub PE plus this epsilon sub PU? It's because that epsilon sub PU assumes it started out at 0. I need to get the concrete back to a 0 stress state where I'm calculating that. That's where that epsilon sub PD is. It turns out when you do the calculations that epsilon sub PD is really small, right? But we'll get into that in a minute. We'll talk about how to calculate it. So everybody kind of see what the 3 stress states are, or strain states are. This one, right, and this curve below here, I wrote that before. It's stressed immediately to this epsilon PE, and it gets stressed a little, or strained a little bit more, if you will. This is epsilon. Oh, that one is epsilon sub PD, and then it gets strained just a little bit more, and then that last one is epsilon PU. Right, and my total epsilon is equal to epsilon PE plus epsilon PD plus epsilon PU. All 3 of them added together. When all 3 get added together, I then know what this value is. Right? This comes from constitutive. Let's take that epsilon down below, I plug it into that Minigato-Pinto equation, and then that tells me what FPS is. Once I know FPS, I can calculate what my T is, I set that equal to my C. It's not gonna work right away, right? Because it's assuming a neutral axis, then I iterate on what my neutral axis is, and it works its way to the answer.
Is there any utility of that weird plot up there other than demonstrating that?
Nope. Just trying to explain what the hell epsilon sub PD is, right? And what strain state we're at in this thing. Right? If we see that, like, it's stretched, I get to the 0 state, I gotta stress it beyond that. This is the right at failure. So that one makes sense. It's this one trying to get it to a 0 stress state is the one that kind of throws me off a little bit. Okay. Yeah.
The positive epsilon PS from the right, is that just for the
That's just the tendon. Yep, that's just what's happening with the tendon. Right? So my tendon is stretched. This is epsilon sub PE. That's this distance right here. And then I decompress it even further. I decompress the concrete, but I put the steel into more tension. There, that's the second one right here. And then beyond there, I strain my steel even more out to epsilon sub PU. Right? Okay, and so that's what's happening, okay? So in this case, like I said, epsilon sub P1 is equal to epsilon sub PE. How do I calculate each of these things? Well, we say epsilon PE is my pre-stressing stress, FPE, divided by ES. Right. My elastic pre-stressing strain is just my elastic pre-stressing stress divided by the elastic modulus, right? That's assuming that I'm in the linear range here, right? This is what ES is. Like that. Right, that's the slope right here in that stress strain diagram. That's what that slope is, and so I can calculate that stress. It's just going to be, or the strain is just going to be FPE, my pre-stressing stress. That's something that's given to you in the problem statement, divided by ES tells me what epsilon sub PE is. Epsilon sub PD, this decompression stress, that's a little bit more involved. You can see, I'll take you on this journey next time. We just have 2 minutes left, but it's a little bit of a journey, but it's not, well, it's actually a pretty easy journey. We have 2 minutes. I'll take you on the journey. We'll do it. So basically, I'm trying to calculate that distance, right? I want to calculate what that strain is there from there to there. So what I do is I just calculate this strain, right? I say, what is the strain in my concrete at this location? What's the strain in the concrete at that location? We have an equation for calculating that, right? The strain in the steel will be the opposite of that. That's what this is. The strain in the steel is opposite of that. Strain in the concrete's opposite the strain in the steel, right? One's in compression, one's in tension. While concrete goes this way to that, the steel, it gets decompressed, the steel gets more tension. That's why it's opposite there, okay? I can calculate the strain in the concrete. So I want to do it now so we don't have to do it next time. So let's see. The strain in the concrete is just the stress in the concrete divided by EC. So this is all the stress, right? This is, you calculate the stress of this, the stress of this first, and once I figure out the stress of it, I divide it by E to give me the strain in my concrete. So I just find my stress in my concrete, I get my strain in my concrete, okay? So then, this is the equation. There's no external moment on this. This is without external moment. This is the equation for calculating the stress in the concrete at that location. That's why it's FCEP. This is the stress in the concrete at the location of the pre-stressing strand, right? Is just FP over AC minus FPEP over SEP, right? I calculate what my SEP is. That is the modulus. Sorry, that's the rupture or what is that thing called? That's called the section modulus. That's the section modulus at the pre-stressing strand. That's why it's over EP, right? And then you kind of plug it into these equations and you can calculate what that stress is. And then once you know what the stress is, so this is the equation for the stress, just simplifying this equation with this substituted in, it ends up with this. That's the equation for calculating what FCEP is. And then calculating the strain is just that value divided by EC, right? So it's just the same thing, it's just we're dividing by EC. And so that is how you calculate right there. That's the equation, I would say that you'd use this equation for calculating that decompression stress. Okay? Study that a little bit and just kind of, it's nothing too crazy to get to there. But then, so your solution process, the first thing you would do, like in your Excel spreadsheet or whatever, you would have a quick little calc. You'd have a calculation for what this is. You just say, oh, FPE over ES would be epsilon sub PE. Then I would have a quick calculation of epsilon PD is what we called it. Epsilon sub PD is equal to this, right? Easily calculated in your calculations. And then the last part is calculating what epsilon sub PU is, which is going to be a function of x, which we'll write down next time. It's going to be a function of where that neutral axis is. And then that's it, okay? And then you set the two equal to each other and find the x that makes it work. Or another way you think about it is you could plot the C on one axis and then the T on another axis, and you look to see where they cross each other. And that's kind of where the strain compatibility thing works out. But we'll cover that next time. Thanks for hanging with me. Most of you for hanging with me. It's a tough one. This is a tough one to talk about because there's a lot going on. Yeah, so this is, right. So the self-weight will kind of, so this is just the capacity of the beam. The demand in this case is going to be on a different, it's on the MU side of things. And so we don't ignore the self-weight. This is just, right now though, we're just calculating the capacity of the beam without anything on it. And then we'll compare that to the demand, which has the self-weight and the dead load and the live load in it and compare. So it's a little bit different. Because the other design was included in the design, and now we've kind of said, let's just look at the beam itself. That's why we just don't look at that external moment. We say, what's happening in the beam by itself? Yeah.
So what do you want for homework? That-ish?
Yeah, that-ish. Yep.
For now?
Yep. However you want to do that.
Did you guys figure out